And yeah, today I brought a friend and guest lecturer, Erin Healy. She's also a postdoc at KICP, and yeah, her job is to build these microwave telescopes that I was planning to talk about, but then she was so nice to volunteer and talk about it herself. So yeah, go for it.
Not for any lack of trust in Christoph's ability to talk about microwaves, but only out of enthusiasm myself. So yeah, thank you all for being here. I have taken a look at some of the slides that Christoph has presented, but please interrupt me with questions if I haven't connected the dots fully. And if you haven't been here every time like I have, welcome. I mean, I haven't been here every time, but okay, great. So let's get into it. What are microwaves and radio waves? So this graphic should look familiar. You have an electromagnetic spectrum that we have a very, very small bit of is familiar to us. We can see just those colors that our eyes have been evolving for millions of billions of years, millions. And we can't see all this other richness to the electromagnetic spectrum. And so you may learn about or have learned about X-rays, gamma rays, and UV. Those are on the higher energy side of the scale. Those are smaller wavelength and higher energy. And on the other side of the scale, we have increasing wavelength. We have lower energy waves. And we're probably familiar with these waves from everyday life. We use them because they pass through things freely. So that's very useful. We can use them for radio communication because they can go through buildings because they're so big. And they can also, as we found out by experimenting with microwaves, they heat up water. The polar nature of water makes them good absorbers of microwaves. Oh, can you guys hear me okay? Yeah. Okay. And then another kind of cool thing that we can do with things like microwaves is they're part of MRIs that we can use to probe structure because they pass through things. And so we have a look at an instrument from 1887, and then we have a modern cell tower, which again these are now everywhere, about 140 years. And we're really using this electromagnetic spectrum. But I'm not here to talk about how we can use microwaves, although that is interesting. I'm here to talk about what microwaves exist naturally and what we can learn from microwaves. So first, let's keep thinking about the relationship between wavelengths and microwaves and visible light. How does that affect our ability to observe features of things? So let's say we have two telescopes. They're the same size. They have half-meter apertures. And one of them is a microwave telescope. The other one is an optical telescope. So we put it on top of the moon, and which one is going to resolve, we put it on top of the Earth, which one is going to resolve the moon better? Anyone want to guess? The optical. These smaller wavelengths are able to probe the structure on the moon with finer resolution. The larger wavelengths don't do as well, as we'll see in a minute. And this is a microwave telescope. This is in the Atacama Desert in Chile on a bad observing day. We'll see better observing days. Microwaves are absorbed by water, so clouds would not be good for this microwave telescope. But there's a half-meter telescope, and now let's ask, with that half-meter telescope, what feature size on the moon would it resolve? How big of a feature could we resolve on the moon? So first, let's talk about the case that we're more familiar with, which is the optical telescope. So that resolves about 500 meters across on the moon. And if you take that same size aperture, but you put microwave detectors in it instead, now you're going to see something like that. The moon is barely resolved. This is not fully fair. This is from early testing with a telescope that will get better sensitivity. But it's blurry. Microwaves, once they get big enough, can't be used to resolve things like the moon. So So what are we looking at? So let's imagine now we are back in the 1950s, and we have this onset of technology, and we're learning how to use technology. And some people who are working at a place like Bell Labs are taking some of that technology and starting to point it up into the sky. So higher sensitivity than we've ever had. And one of these examples is this Holmdel dish, which it still exists in New Jersey. And that was used, you can see it's on an axis and it can rotate. So it was used to observe all throughout the sky. And it's tuned to a 3 Kelvin signal. It's tuned to microwave signal. And it picked up 3 Kelvin. So that's a power, that's how much the amount of signal there was. And that's kind of a small amount of signal. We live at 300 Kelvin. So it was pesky. I was like, where is this 3 Kelvin coming from? It's not that big, but no matter what we do with our telescope, we can't get rid of it. They thought that it might be some of the droppings of the birds that had taken residence in this giant horn. That wasn't it. The thermal radiation of whatever that was not the cause of it. They thought it might be from New York City. They weren't that far from New York City, so they really tried to isolate the noise from New York City, and that didn't make a difference. So they spent months, if not years, trying to figure out what this signal was. And now we'll take a detour to people who were maybe trying to predict this sort of signal. So you guys have learned about Einstein and his contribution to how we understand gravity. And you've also learned about Hubble and how he discovered that the universe was expanding. And so what do these things say together? So first, let's take them one by one. So what did we learn from Einstein? The power of the Einstein equation is that it enables you to take the space-time geometry, so just the geometric features of a space-time, and relate it to the energy contents of the universe. So if you know one, you know the other. That is powerful. We can make measurements of energy, we can make measurements of geometry, and we can understand how these things relate on giant scales. So Einstein, really, when he wrote down this equation, didn't even understand how it would be used to describe the entire universe. But pretty quickly, people learned that they could just apply this to the entire universe. If they made a few simple assumptions, then you could ask questions about what is the entire makeup of the universe? What's the shape of the universe? And so this was now making predictions, or making testable predictions. So now we can go out and look for evidence of these testable predictions. And at the same time as people were starting to make testable predictions, one helpful feature of Einstein's theory was added in, an extension of Einstein's gravity to our universe, and that allowed the universe to expand. It just added the parameter that said, what if the universe can sort of ebb and flow? And when Hubble, who started in Chicago before doing work in Southern California, which is where this data was taken, he was measuring objects that he could measure not just their distance from their Earth, but also their velocity away from Earth. They were mostly receding away from Earth. And that seems to say, okay, everything's moving away from us. The further things are away, the faster they're moving away from us. So that's interesting. And so then what does that suggest? So you don't need to know Einstein's equation to try to roll back the clock and imagine what would happen if the universe that we have now, which is mostly at 3 Kelvin when you're not close to the surface of an Earth, if you condense all of the makeup of the entire universe into a smaller volume, what's going to happen? Things are going to get hotter, things are going to get denser, and someone jokingly called it would be like a Big Bang. Well, the name stuck, and this was, again, a testable theory. Now, if this happened, if there was some sort of phase transition where we went from being sort of modestly dense to super dense, that would emit radiation. And that radiation would still be around, unless, you know, it was so weak, but hopefully it would still be around. And so down the road from Homedale, New Jersey, at Princeton, New Jersey, Bob Dickey and crew were cosmologists trying to predict this signal so that they could measure it. And famously, they got a phone call during their group meeting, and they picked it up, and Bob Dickey said, "Boys, we've been scooped." Because the Nobel Prize went to the other guys. They had predicted the signal, they knew why it would be there, but the radio astronomers had measured it, and they were the first to find the next I should say to open up the next phase of cosmological study. And so that was 1965, and when Bell Labs instrument was observing and they were using this fancy technology, riding on telecommunication, it didn't quite translate as well to for the next 40 years. We didn't get tons of better and better measurements of the CMB, except that we've ruled out what now we consider sort of crazier universes. So there were lots of theories about what the universe might have been early on and late. But for the last, say, 30 years, we've had a pretty consistent model of the universe, and we're gonna see where that comes from. But it all starts in 1965. Okay, so what is this? What are the features of this signal? So let's give it a name in this. I'll refer to this as the cosmic microwave background. So that is the theory predicted by Bob Dickey's group, that there'd be a thermal relic of the Big Bang. And so based on what we know about abundances of elements, what we know about features of the universe, we can put constraints on what we would expect the signal to look like. And this was basically what was predicted. Now this is actually just a measurement, and the error bars are so small that you can't tell. But this is about a 3 Kelvin signal. It's been actually shifted a little bit due to effects of the universe. But this is the peak of the cosmic microwave background spectrum, and the shape should look familiar. I think you have been introduced to black body spectra, and so that's a black body. Do we know what a black body, what the feature of a black body is? If anyone has any intuition, black bodies are sort of like one temperature that emit lots of frequencies, but sort of you can be described by a single temperature. They're this really simple, almost mathematical object that the whole spectrum can just be described by a temperature. And there's one most perfect black body in the universe, and that is the cosmic microwave background. And it started much hotter. I keep saying this 2.7 or 3 Kelvin, but it started much hotter. It was a dense plasma where all of the energy contents of the universe were located, were confined to. And but as we've also learned, the universe has been expanding, right? So as that light has been traversing through time and space, it's been getting stretched by the literal space-time itself expanding. And that expansion causes the waves to redshift, so they go to lower frequencies, and now they're shifted into the microwave. And so thank you to Christoph, who has made some really cool animations. But here's where this black body has moved as the universe has expanded. So it started out as a much shorter wavelength, higher energy, and then it's just totally chilled out over 13.8 billion years. So that's cool, right? Like the fact that the error bars don't even extend past that line is like really cool. The early universe was something, but also like where did we and everything else come from if that was what we looked like 13.8 billion years ago? Like how did anything evolve? We all had ideas that, oh, you have some sort of kernels of structure that then gravity works and then that builds bigger structure. But if that's what the universe looked like, then we have something entirely wrong. But this is where instrumentation to the rescue. Because if we had stopped with the technology of 1965, then we wouldn't have an answer to that question. Yes?
So on the black body radiation curve, as I understand it, every one of those, every wavelength would, in quantum theory, would correspond to an individual quantum of light that reaches your detector. And when we talk about the interaction of light and matter, we know that each atom has a characteristic series of energy levels, and a different photon wavelength corresponds to each jump. And what I'm asking is that spectrum truly continuous?
Right.
In other words, there's no wavelength? There would have to be an infinite number of, if it were continuous, there'd have to be an infinite number of energy differences.
Totally. Your intuition is exactly spot on. If you look at like tungsten, which has tons of energy levels, you can see almost a rainbow. You can see lots of spectral lines, but there's huge gaps. But remember, this is the entire energy of the universe. So it's chaotic as well. There's lots of motion. We'll learn soon. There's actually lots of motion. So there's sort of lots of available energy states. There's sort of every conceivable energy difference in that sense. It's many available electronic states such that you can produce a truly continuous spectrum. But it's the exact right intuition. We don't have objects that behave like this typically. It's a radiation that does not behave like astrophysical objects usually do. So it's very special. And it's very compelling. That's why we kind of knew what it must be, because nothing else behaves like this. This spectra doesn't look like anything else. So great question. But as I said, there is structure buried orders of magnitude below what this measurement showed. So, yes, please.
The peak here is about 5 centimeters.
Yes.
And the peak of coming from our sun would be about a half micrometer. Okay.
Sorry, what's the half?
The peak of the
I don't.
of the sun.
Not a stellar guy.
Plus minus 10%.
Okay.
Doesn't matter, okay. So in this case, this is displaced from half a micrometer all the way to 5 centimeters.
Yeah, that's right. It's. I don't know if this. How hot's the sun?
6,000.
Yeah, so that's similar to the early universe. Yeah, so yeah, it would be similar to the expansion of the universe has expanded so much that we've gone from half a micron to centimeters.
This would be really
The sun would be that way.
This
Yeah.
would be a shift in the
Yeah, exactly. So cool. So great questions. Okay, so now I've kind of thrown them all at once, but we can take stock to appreciate 50 years of technology improvements. So in 1965, this is what Penzias and Wilson basically would have seen. They did not get a full sky map. The Earth gets in the way, the galaxy gets in the way, things get in the way. You can only do full sky maps from space, so that's just a false but representative map of what Penzias and Wilson would have seen with their telescope. And that stretch that's right through the middle is not cosmic microwave background feature, that's the galaxy. And you can see that then in all of the other satellite telescopes. And that's noise. There are people that study the galaxy. I'm not one of those people, so we're just going to remove it. And this is the cosmic microwave background. We do have higher sensitivities where the galaxy is not, but things move around enough that we have full sky maps of the entire CMB, as we call it. And so you can see, 1965, single temperature, 1992, very, very exciting satellite result from the COBE mission, a NASA mission, and that was the first sign that, there's actually structure here. You have to go 5 orders of magnitude to more sensitivities, which is why there's a big jump between 1965 and 1992, because to get 5 orders of magnitude in improvement in technology does not happen overnight. But once we got those 5 orders of magnitude, then in 20 years we could massively improve our measurements. So in 2003, WMAP, another NASA probe, made this measurement that Lyman Page, one of the leaders of that, calls a baby picture of the universe. And then in 2013, ESA, the European Space Agency, released Planck, which has the finest full sky, highest resolution full sky maps to date. But the story doesn't end there because I don't work on satellites. We don't have to do this from space. So there's a very there's a new frontier of cosmology. And so now we're going to say goodbye to Planck. It's going to be probably another 20 years before anyone's willing to spend billions to get a better picture of the CMB. So we're not waiting. We're doing things from the ground. And we have good reason to do so. Because if you sort of go to the very edge of the Earth, somewhere that's super high into the atmosphere and super dry, so there's almost no atmosphere and no buildup of gases, then you can actually see through right to the CMB. You can't get a full sky map, but you can get higher and higher sensitivity and resolution. So to back up, there are multiple options. You can do this not just from satellites. You can also do it from a balloon, which is also sort of cheaper. Millions, not billions. But you still need NASA, so it's like a little clunky. But these are also, they have some limitations. They have to be reduced in terms of their power. You can't use as much electrical power in space as you can on Earth, where you can basically burn as much diesel as you want. Not that that's what we aim to do, but we can. Everyone's switching to solar, which is super good. But if you put a solar panel and batteries on a satellite, you're still going to be limited to get to the sensitivity you need, because as I just mentioned, we're at these 6 order of magnitudes lower than sort of just this monopole uniform signal. So you need these hyper sensitive detectors, which we'll learn soon require lots of accessory electronics and cooling power. So these things add up to the cost. And another really important limitation is that you can't build an infinitely big dish or mirror aperture. You can't build something that is 6 meters in diameter to capture the finest angular resolution where we think interesting things might be. And so we have to consider other options. And so that's what takes us to the Atacama Desert at the top of a mountain at 5,200 meters. And to give you a sense of sort of how going to different elevations or what the atmosphere does as wavelength changes, so we can see that there's this 100% transmission and then there's these dips. And you want to put your telescopes where the dips are. And so what we really want to measure is right here. And if you go to the Atacama Desert, these dips basically drop to 0. And so you get these 2 pristine bands that are exactly where the CMB peaks. So if you ever see cosmic microwave background data anywhere, you'll often see it in 2 colors, because we have these 2 channels that we can see very clearly from Earth. And we're also building more telescopes at higher altitudes to get even higher sensitivity. But let's see what that gets us. So here is the Planck telescope where we saw the full sky map, which looked super resolved. But when you blow it up and look really closely, you see that it's actually pretty noisy. There's a lot more speckles in it. That's characteristic of noise. Whereas if you look at it from a 6-meter telescope from Earth, and you use that to resolve the features, we can see the smoothness of the CMB really come out. And not just that, we see features just pop out. These are galaxy clusters that the gas of the galaxy cluster has been interacting with the radiation. And so they pop out of the maps. And so now there's a ton of science we can do that's at the galactic scale.
This is a map of radiation.
Yes, this is like a 90 gigahertz map. So it's like looking at a specific frequency of light, and then the I should explain that the red regions are overdensities, so those are above the black body temperature of 3 Kelvin, and then the blue or the underdensities, the colder regions where the temperature is below the 2.7 degrees Kelvin. So that's a map of the temperature of that radiation.
Do you have any spectrum representing a black body at like 4,000 degrees, 3,000 degrees, and to compare?
Yes.
How would that evolve?
That is what this is. So this is changing the temperature.
Okay.
This is as the temperature is increasing, the wavelength that the spectrum peaks is getting bigger, and the spectrum is broadening.
So in this case, these spectrums are really from a lower temperature body. The ones that
Yes.
are longer. Okay, so if they are related to temperature,
Yes.
could they be related to something other than temperature?
We can, temperature is basically the density of the radiation. So we can describe what the frequency of the radiation is. We can describe the temperature, which is density of the radiation. We can describe polarization, which is beyond the scope of this course. But we can describe sort of a bunch of different features of the radiation, temperature being one of them. And not all objects can you just give one temperature to describe the whole spectrum, because that's only of black bodies. So it just happens that we can do that.
The 2.7 Kelvin degree
Yes.
is really the temperature of the universe.
Yeah. Yes. Yeah, of empty space. That's what you'll be at 2.7 Kelvin. This radiation fills. It's the only thing in empty space, and so it's the only thing keeping you warm at the end of time. Something comforting, I suppose. Okay, one last quick thing before I hand it over to Christoph. Oops, I'm going too far. I just want to give a quick sort of look into the modern microwave detection. So in addition to building bigger telescopes, which enable you to make higher resolution measurements, so that's what this telescope is even bigger than that half-meter one. Why even look at that one? Look at this. This is gigantic, and we can resolve really, really fine images on the sky. But another thing that's going to improve our ability to do science with these detections is the sensitivity. So that's how much of the signal are you actually capturing, and in our case, we're really trying to find the difference between those temperatures, between the high and low portions of the maps. And so we're using now, we don't have Bell Labs, but we can utilize advances in quantum computing to realize higher sensitivities. And here's a little plot that can give you some intuition for what we do. So if you have heard of superconductors, you might be familiar with this type of material. That some materials, like aluminum, they just are superconductors, but you'd never really know unless you cooled them down below their superconducting point, at which point they stop behaving like a normal metal, which conducts but doesn't conduct perfectly, and then all of a sudden it conducts perfectly. So this is why quantum computing is so interesting. One of the reasons, it's really like fast transmission, because there's just absolutely no resistance. It's a different regime of how materials behave, and we can leverage those behaviors to do science with them. And so here is the red curve is showing the resistance. So how much does the metal heat up as you put current through it? How much does the metal just straight up conduct versus sort of soak up some of the energy as it conducts? And so we've got normal resistance, where we've got a metal behaving normally up here, and then we have this super, super steep drastic drop down to a super low temperature that happens at the critical temperature, and what you can do is put a detector, design a detector that sits right at that edge. And then the tiniest little change in temperature is going to shoot up the resistance, and now we're going to have amplified what that really, really, really faint cosmic glow is into something we can actually measure and then turn into usable data. So stay tuned. Simon's Observatory is on its way. This is the telescope I work on that is going to be sort of the next best microwave maps until CMB S4, which folks of Chicago should be familiar with because it's being funded mostly out of Fermilab, and many of the people at UChicago are very much involved. This is like 100 millikelvin, so 0.1 degree Kelvin. So very, very close to absolute zero. And this is why you can't do this in space. To get something that cold requires tons of power, which you don't have enough of in space. Okay, hopefully I've left enough time for Christoph to give you a little bit more about radio waves. So thank you all very much.
Thank you. Then now I want to spend the last half of this lecture to talk about the other big thing you do with radio waves. And this also started in the 60s when people started pointing radio dishes at the sky, and they found these things they called radio stars, which is just something in the sky that emits radio signals. But the problem, as Aaron mentioned, is if you want to figure out what exactly these are, the problem is that with radio waves you have a lot worse resolving power than with an optical telescope. So, for example, one of the telescopes they used back then is the Parkes Radio Observatory in Australia. And if you kind of do like a back-of-the-envelope calculation of what's the resolution you can get with this, it's about 0.05 degrees, which is about the 10th of the size of the moon. So if you basically now took an optical telescope and you looked into this area, you would actually see a lot of stars, and it wouldn't really be possible to figure out which one of those is your radio source. But this guy here, Cyril Hazard, had the pretty brilliant idea to get a better resolution on this, and he discovered that by just pure chance, if you were observing one of these objects called C3C273, because the University of Cambridge, that's what the C stands for, made these catalogs of radio sources they discovered. And this was in their third catalog they made. This was the 273rd object, so that's where the name came from. Very creative. But he discovered that if you viewed the source from Australia with this Parkes Radio Observatory, then just by pure coincidence, the moon would actually move across this radio source. You would kind of get something like an eclipse. And this was actually what's going to happen twice within like a month or so. And what he did was he just pointed this radio telescope at this radio source and waited for the moon to come. And this is from two measurements from the 2 times the moon passed. And just from looking at the time when this radio source disappeared and when it appeared again, you could then calculate where exactly it should be, because we know the position of the moon very, very well. And he also discovered something else that's kind of interesting. You can see there's this little bump here, and there's also this more pronounced bump here. And from this like kind of feature here, he could conclude that actually this was not just a single source, but there have to be 2 sources that were like a little bit apart. So this bump here is from kind of the moon, moving past the first part of the source, and then a little later it kind of gives room to the other source. And this way he could determine the position of this radio star much better. And this guy, Martin Schmidt, then pointed a telescope at there, and he didn't discover a star, he discovered a galaxy. And so he figured out, okay, I'm just going to take a spectrum of this galaxy, and we learned that spectra are a very powerful tool to figure out what's going on. And he looked at the spectrum, and it just basically didn't make any sense to him at all. And he was really confused about this for quite a while, until he figured out that actually this was a perfectly normal spectrum. The only thing is it was just redshifted very, very extremely. So this is kind of what it looked like. So the top is his measurement, and because telescopes are perfect, a lot of lines are kind of hard to see, but you can see these like 3 prominent lines here. And those are from hydrogen, which is very common. So these are kind of your bread and butter lines you will look at. And this is a spectrum you would compare them to. And the same lines are kind of at these positions. And you can see this is offset by quite a lot. So this source had to be redshifted by a lot. And if we look back to the Hubble relation, where the further galaxy is away, the more redshifted it is, we can estimate where this galaxy should be. And that would be about 1.5 billion light years, which at the time was basically how far you could look with optical telescopes at the time. So this was really weird because this radio source was pretty bright, but it was also extremely far away. It was one of the furthest objects that had been discovered at this time. So the question was, how could something this far away emit so much radio signal that it would still be this bright? And it got even worse because they also discovered that the brightness of the source changed within a year or so. So this is kind of, if you just measure the brightness of this radio signal again and again, and you can see that within a year or less, it can vary drastically. And if the source was like this entire galaxy, that shouldn't be possible, because if you imagine like you have a galaxy and then just from one moment to the other, all the stars just kind of shut down, you wouldn't actually see all the stars shut off at the same time, because a galaxy is tens of thousands of light years across. So all the light from the stars would arrive at different times. So the stars closest to you would look like they shut off first, and then the light from the further stars would still be on the way. So if you measured the brightness of the galaxy as a whole, it would just kind of slowly fade away. It wouldn't just suddenly disappear. So because of this, you can conclude that this source it cannot be the whole galaxy. It has to be a fairly small part of this galaxy. It has to be something like the size of a light year or so. So that was really weird. So you have some really small object that for some reason can emit an extremely bright radio signal. And it took a while to figure out what this was. But in the meantime, this guy, Martin Ryle, had a different idea, and he said, okay, we may not know exactly how these work, but we know one thing, and we know that they're really far away. And even this relatively bright radio source is one of the furthest objects we know of so far. But there's a lot of others that are actually even fainter, so probably those are even further away. So if we just take these radio sources, we can actually look back in time much, much further than with the optical telescopes we have right now. And he figured out that actually, if we, these radio sources, they're not going to have all exactly the same brightness, but if we say, okay, the variation between them isn't going to be too extreme, then we can say, okay, if we live in a static universe that is infinitely old and it's basically the same everywhere, we can predict how many of these radio sources we would expect at certain distances. And of course, you see more radio sources the further away you look. But overall, we can predict the brightness distribution we should see if the universe didn't change basically at any time. But if we have something like a Big Bang where the universe was different in the past, then we might actually, there might be more of these or fewer of these in the past than today, or than in at more recent times. So then, for example, if there were more of these in the past, we should see more of these weaker sources than of those brighter sources. And that's what he did here. So this is these are basically both are the same basic idea. It's just he looked in different parts of the sky, and this is just showing the brightness of these radio sources compared to how many of those there are. So you can see there's the very bright sources are pretty rare, and then the fainter and fainter you go, the more of those there are. And if we live in this infinitely old universe that has been the same basically forever, then we would expect this curve to kind of follow this straight line here. But you can see it's actually, it's very different from that. So there are much, much more of these fainter sources that we would expect in an infinitely old universe. So this tells us that these sources must have been more common in the earlier universe. And this was one of the good pieces of evidence that the Big Bang is probably a good theory. Of course, the CMB is an even better probe. And today, we can actually identify which galaxies these radio sources are in. So instead of just kind of doing this vague, like, okay, they're probably, the brightness is probably related to the distance, we can just identify which galaxies they are in, and we can directly measure the redshift of these galaxies. And then we get something like this. So this shows you relative to the redshift. So the Z is just telling you how redshift it is, so how much longer the wavelengths are than what you would usually have. So the more to the right this galaxy is, or this radio source is, the older it is, the further away it is. And then these show you kind of how many of these there are. So the red bar here, that tells you kind of like all of these radio sources, which are called AGN, and we will get to what these actually are in a bit. And you can see they are much more common in the early universe. And if you only pick the very, very brightest of these, it's even more extreme. So that's this dotted line here. And they basically only, there are basically none of these relatively close to us. So these really only existed in the early universe. So there must be, the universe must have been different in the past. But, okay, so what are these actually, right? That would be interesting to know. And for that, we need to find a better way to resolve, we need to find a way to get a better resolution with our radio telescopes. And Martin Ryle was actually one of the pioneers of this technique, and he ended up getting a Nobel Prize for figuring out this technique called interferometry. And for this, I have to talk about math a little bit, but bear with me. I promise there's going to be only one equation, and it's a pretty simple one. Okay, so we need to think about a kind of weird way to think about data. So let's say, I have some data here. This can be whatever you want it to be. This can be a stock price. It can be, I don't know, the temperature over the last week. It can be some random numbers that I made up just to have a pretty line. And here's a cool trick we can do. We can just take sine waves here. So here I just pick sine waves, and here I add them all up. So this will show you the last sine wave I added, and this will show you how the sum of sine waves, so the blue line is how all these sine waves that I added together look like. You can see that it pretty quickly looks very, very similar to this data I originally had. And so what I can do is I can just kind of, instead of storing this data itself, I can just basically figure out, okay, which of these sine waves do I have to add up? And for each sine wave, I just basically remember, okay, well, how big does this wave have to be? And that's basically what I show here. So this shows you for each wavelength of the sine wave, how big is the amplitude of the waves that I add. And there's also a second number that basically tells you kind of if this, it's called the phase. It basically just tells you if this sine wave has to be shifted a little to the left or to the right. And this process is called a Fourier transformation after a French mathematician called Joseph Fourier, who lived like in the 1700s, I think. And so what I could do instead of thinking of data as just having, for example, if this is a time series, just having this value at that time, I can also just remember which wavelength do I have to add up to get this data back. And this is actually something that we use pretty much every day. Back when I was a teenager, this was kind of the really cool thing to have, an MP3 player, because you could store like 20 songs on this thing, which was amazing at the time. And the reason you could do that is because you probably noticed that after a while, like this doesn't really change much. And if you look at the amplitudes of these wavelengths after kind of here, these really don't matter much. So instead of just storing all these waves I have to add up, I just pick the most important ones, and the rest I just leave out. And it's you can see there's like a little bit of a difference, but like you're not going to hear this. It's it's going to give you this. The song is still going to sound pretty good. So it is actually in practice a lot of the time you don't actually need like the full information. You just need to make sure that you have all the important parts, and then the rest is kind of something you can ignore. But So what we can do is we take the song, so we take this electrical signal that has to be sent to the speaker. We just calculate which waves we have to add up. Then we store this on our MP3 player, and then we want to play it back. We just read this data, we add up all the waves together again, and then we get our signal back, and then we can listen to the song. The problem, of course, is we first need to figure out, this part here. Which waves do we actually have to add up? So for this, let's take a simple example. So I can tell you, this is just 3 different waves I added up. And so if you want to figure out which wavelengths these are, if I look at this and I pretend I don't know the answer, I would say, it looks like there's a wave in here that kind of looks like this, right? You can see it going up here, then down, and again. So if this wave is actually one of those ones that I added up, then where this blue wave is large, then the orange signal should also be large. And where it's negative, it should also be negative most of the time. So what I can do is just at every one of these points, I just multiply these 2 signals, right? I take the blue curve here times the orange curve and so on, and then I get something like this. You can see that actually overall, what I get tends to be positive instead of this thing here, which is about roughly 50-50 positive and negative. So if I pick this blue line correctly, then on average, if I multiply those 2, I should get the average of this should be larger than what I would get if I just picked the wrong wavelength. So I can just kind of do this test for every wavelength I think might be in there, and then I get something like this. So this is orange is again our signal. Then the blue line here is the wavelength I want to test. Then I multiply the 2. Then that gets me this one. And here I just basically put in the average of this waveform or of this signal for depending on what wavelength I picked. And so if I pick correctly, you can see soon here, now this is the correct one, and now I get a big average when I multiply these. And this is actually what is called the Fourier transformation, where you calculate which of these which wavelengths are in my signal. And there's going to be this third one coming up soon, so you can kind of, if you pay attention, you can see this suddenly all getting positive in a bit. There we go. And so I can, this is how I can figure out which the different wavelengths are in my signal.
Question.
Yes?
Are you saying that in terms of this data, instead of retaining the actual data, you look for a transformer and you retain the transformer as
Yes.
opposed to the original data?
Yes.
Doesn't that bias your interpretation of the data later?
Not necessarily. So in principle, what Fourier has actually shown is that unless you have like some really you can make up some really weird cases where this is not the case, but for all practical purposes, like this transformation is exact. Like you can get, if you actually save all the wavelengths that are in there, you can get the entire signal back. You can transform back and forth as much as you want, and you will still retain the same information. If I do the thing with the MP3 and I kind of throw away some of that information, then that could bias me. That's true. But there's also, the thing is, I can also kind of tell, depending on what wavelengths I throw away, I can also kind of tell what information I'm losing. So for example, if I want like very fine details, like something that changes very quickly, then that's going to be encoded in the very short wavelengths. Right? So if I throw them away, I'm going to kind of lose a little bit of the detail, and I need to be aware of that. That's true. Okay. Now I can also do these Fourier transformations not with one dimension. I can also do it with 2 dimensions. So this is a picture of a guy, Joseph Fourier, and these are, now I just don't have just a one-dimensional wave. I have a bunch of 2-dimensional waves. So this is just the brightness information, and I just add these all up. because this is a picture which contains a lot more information, I have to add up a lot more of these. But you can see that pretty quickly I get something that's really close. And if I let this run up for longer and longer until I have all the important waves added up, I would again get the exact same result. And this is also something we use in basically every day, and that's the JPEG, which stands for the Joint Photography Expert Group. So if you want to store a picture, you can do the same trick as with the MP3, where you just kind of figure out, okay, which wavelengths do I actually need? And then I can kind of throw the ones away that I don't really need. So these are 2 times the same picture, basically, but one of them is only 1/3 the size of the other. And I don't know, anyone want to guess which one? You can tell if you look very closely, but it's really, really hard to tell. So yeah, this picture is actually less than 1/3 the size of the other, because I got rid of all these like very fine details that I don't really need. And it's really hard to tell the difference. And this kind of a lot more bells and whistles to this JPEG format, but that's kind of the process at the heart of this. So let's recap this whole thing. The important points are, if I have some data, I can always just kind of reproduce this data by just adding up a bunch of sine waves. And instead of just storing the data itself, I can also just store which of these sine waves I have to add up. The way we determine which of these sine waves we need is we multiply the original data by the sine wave, and then we take the average of that. And I can also do this with 2D images. I can do my JPEG thing. And for practical purposes, a lot of the time it's fine if you lose some information, as long as you make sure that the part of the information that you actually need is in there. So now let's try to apply this to radio astronomy. So we now can do something called interferometry, where instead of just having one giant dish, I have a bunch of smaller radio antennas. So this is something called the Very Large Array, which is down in New Mexico, I think, in the desert. And if I just take 2 of these radio dishes and I just point them at some source, then they're going to be some distance away from each other. So my source is here. Then the radio signal is going to arrive at this antenna a bit earlier than at this one, right? And now, if I just kind of filter my radio signal, so I have a very specific frequency, then depending on where exactly the source is, there's going to be some time shift between these 2 radio signals, right? So imagine the blue one is the signal at one of these antennas, and then the orange one is the signal you get at the other antenna. And then depending on, if you imagine like you move the source, then these are going to get kind of shifted relative to each other. And now what I can do is I just kind of combine these 2 signals, and I just multiply these with each other. Then I get something like this, right? If they align perfectly, then I multiply a positive number with a positive number, I multiply a negative number with a negative number. So I get a pretty big signal overall. If they're completely out of phase, then I multiply a negative number by a positive number, so I get something negative. So if I take the average of this multiplication here, then I can. This basically tells me how in phase these are, right? If they're perfectly in phase, then I get a large number here. If they're perfectly out of phase, I can get a negative number. And this probability, this property where this is called the visibility. So what this tells me is, if I have a source at a certain position in the sky that produces a certain time difference between my antennas, then this is basically what value I get for this product of the 2 radio signals. And the time difference is related to the distance between the antennas, and it's also related to the exact position of the source. So if I know there's only a single source, then what I could do in principle is I can add an artificial time delay, And I could just measure for which time delay do I get the biggest signal when I multiply them. And from that, I know the time delay between the two signals, and from that, I can calculate where exactly the source is. And you can also see, the further apart I put these antennas, the more precise this is going to get, because for a certain, for a certain movement of the source, I get a much, much bigger time delay. But in practice, most of the time, you're not going to have just a little single point source. You're going to have like some picture. And what you get then is basically, if you imagine there's a ton of sources here, then for each of these sources, you would have to multiply the brightness of the source times the value of this visibility corresponding to the position of the source. And what you would actually measure is the average of all these multiplications. And this visibility is, again, a sine wave. So we have some brightness data here that we're multiplying by the sine wave. And this is what we did earlier when we calculated which waveforms are in our data set to do this Fourier transform. So what I'm actually measuring with this is I'm measuring a certain, what's called a Fourier mode, the amplitude for a certain wavelength of this picture in the sky. And what I can do now is I don't take just two antennas. I just, the very large array has, I don't know how many, a bunch of antennas. So I can just form a bunch of pairs between these. I can just combine all of these. And each one of these antennas is going to allow me to measure a certain, the amplitude or the magnitude of one of these Fourier modes that I then can combine to get my picture back. And what's even better is the Earth rotates, so the kind of part of the array that's pointed towards the source changes. So effectively, over time, the distances between the antennas also changes. So if I just wait a little bit, I can measure even more of these Fourier modes. And kind of like with this JPEG thing, if I just make sure that I position my antennas correctly so that I get all these important waves that I need to get a good picture, I can actually get a really, really good picture now. And the resolution of this picture then is actually not limited by the size of any one of these dishes, but it's limited by the maximum distance between these antennas. And with a very large array, what you can actually do is you load these dishes up on this little kind of cart thingy on rails, and you can just put them at different positions. You cannot put them anywhere you want because you need cables and stuff, but you can change the layout depending on what kind of picture you actually want to take. Now, if I want to get kind of the best resolution picture I can get, then I would build something like the Event Horizon Telescope, where I just, put my radio telescopes at different ends of the Earth. So, they have one at the South Pole, one in Greenland, pretty close to the North Pole, then a bunch of them at different positions. And the cool thing is, with technology today, I can just basically write all the data at each of these telescopes to some hard drive, and then I just put the hard drive on a plane, get them all in one position, and then I just have computers run over it, and I can just do this whole calculation of what the picture is I would get kind of in post-processing. And with this, you can get amazingly good resolution. So this is a pretty famous picture of a black hole at the center of a nearby galaxy. And just to drive home just how amazing the resolution is you can get with this, I got this from Wikipedia, but it's just way too cool not to show. So you have the moon here, right? And remember earlier we could just barely see the moon with a single dish telescope. Now, if we zoom in further, we can kind of see craters. If we then zoom in further, we can see even more details, zoom in further. Now, this is what the Apollo landing site looks like from an orbiter. If we zoom in further, we can see an astronaut holding a little picture of this. And this is actually the resolution. So you could hold up a picture of this on the moon, and you would need a radio telescope, but which is kind of difficult to see a printout, but you can, this is an amazing resolution. And with this technique, actually today, radio telescopes are just resolution-wise the best telescopes we have. Yes?
So those, the New Mexico array, those are all pointed in the same direction for your observations. How accurately or precisely, perfectly aligned do they have to be before you start getting some
Surprisingly, actually not that well, because with these telescopes, they have, because of their size, actually what you're seeing is, you're not pointing them at like a tiny part of the sky, but you're actually pointing them at a, as we said, like something like the 10th of the size of the moon. So as long as your source is in there, as long as you can hit that, which is fairly easy today, it's fine. So it's actually kind of surprising how bad you can be at pointing a telescope with this. Yeah?
So with this technique, are we seeing just sort of the grayscale, the intensity of the light, or are we also able to resolve different colors of the light?
Well, I mean, so this is basically just at one frequency, but you could repeat this for different frequencies. It's just like the amount of data they had to go through to do this was kind of insane. So it would be pretty expensive. Even just like the computing source, like just the power to run the computers would be pretty expensive, and it's probably not worth it. But in principle, you could do this, yes. Okay, so now we got a really cool telescope where we can see really fine details. So let's get back to these radio stars and see what they look like. So if we now look at our old friend 3C273, we see something like this. So we see kind of a very bright source here, and then we see something coming out here, which is, okay, this is kind of not that spectacular. But there's this very similar source, and that looks like this. So this is something called Cygnus A, which is one of the brightest sources or radio sources in the sky, also known as 3C405 because it was in the same catalog. And what you can see here is that here you have kind of a little thingy, and then you see these two jets shooting out, and you get these giant lobes here. And what this is that in the center of this galaxy here, you have a supermassive black hole that has something like millions of times the mass of the sun. And you just have material falling into this black hole. And a lot of it is just gonna fall into it and just gonna kind of disappear. But actually a part of it is just gonna shoot out. And so you just have these giant jets of matter just going almost at the speed of light. And so if you accelerate charges a bunch of times, that's going to produce a radio signal, and this is actually what these radio stars are. And this one is this one is kind of pointing perpendicular to us, but there's also some where one of these jets is basically pointing right at us, and those can be extremely bright. And it actually turns out that very likely it's not just light and radio signals that are coming from this, but also particles like nuclei that can reach incredibly high energies, and that's what we're going to talk about next week. Thank you. Yeah?
My questions had to do with polarization of the microwave background. And so I know there was a big survey going on. So is that survey still going on? What does it tell us? And why is the microwave background even polarized?
Okay, great question. So Christoph and I discussed it, and we decided we would need like another 10 minutes to do polarization. But it is super interesting. So the reason why the cosmic microwave background has polarization is just that it is electromagnetic light. So like all electromagnetic light has a direction to the wave. And it's just a matter of like when you have a bunch of radiation, whether the polarization forms any patterns. And so if you do the math of the early universe, it, like the field theory and called the lambda CDM model, which is basically the Big Bang model. And so if you use that model, you're going to have two types of polarization. One is what's called curl-free polarization. So the polarization only diverges. It's like sources. And then divergence-free, so no sources, it only kind of curls. Oh, thank you. It only kind of curls around. And so those the divergence type of polarization signals, those are sourced from thermal fluctuations in the early universe, density fluctuations. So those seeds of structure that we saw, those small features in the cosmic microwave background, are theorized to be the result of quantum fluctuations in the early universe. And so if all of that is true, then you would have these density fluctuations that would create this divergence mode polarization. Or if you had tensor fluctuations, which means you have like actual perturbations to the space-time itself, if you have those types of perturbations, then that produces the curls. And so that we have not been able to measure from the early universe. And the reason why there's so much effort to study the polarization of the CMB is the temperature and the divergence type polarization, they're really correlated because they are sourced from the same types of things, density fluctuations, temporal changes in density. And then on the other side, these tensor perturbations that cause curl in the polarization are completely theoretical. They have not been detected. And if you had a major gravity event, such as the thing called inflation, but if you had the universe expand super rapidly in the early universe, you would expect a background of these curl type polarization modes. So we're about half the cosmic microwave background like budget right now is going to trying to detect those. B mode is the name of the curl type polarization. So yeah, great question.
Yeah.
I recently read that Penrose was saying that there might be something in the background radiation CBOE, a pattern that might be regarded as maybe an echo of a former universe or something like that. He was talking about that. You know anything? I think it was Roger Penrose. Prominent in talking.
Could be inflation. Could be. I don't know.
The only thing I can think of that Penrose, the only thing I can think of that, okay, so Penrose is super theoretical. He came up with a way to conceptualize black holes that is quite instructive. And in part of his theory, there's also the potential, I think this exists in other theories too, but there also exists the potential for things like white holes, which are, where matter is ejected instead of sucked in. So there's like all sorts of extensions to sort of standard physics that involve, exotic types of astrophysical features. And so the idea, I'm not sure in particular what Penrose said about other universes, but there are many notions of multiverses and sort of impressions of other universes. To my knowledge, there are no, theories that so we can't see beyond the CMB. The CMB is like a cloud, and everything before it is opaque to us. And so I don't know of any theories that say we have evidence of like a multiverse in the CMB. But we continue to make higher precision measurements to try to parse away the signals from the early universe. So we can hopefully get further back with things like B-mode polarization, but I don't think we have any hopes of seeing signatures of a multiverse because there's no theoretical framework for what impression that would leave, as far as I know.
Yeah.
Correlating amplitudes, this very right?
Yeah.
Look for interference there. But there's a technique I've heard about. I'd like you to explain it a little if you could, because I don't completely understand it. Where you're correlating intensities, the Henry-Brown twist stuff. You got a way of explaining why that works? How do you get the size of stars?
Yeah. Well, I have to remember how that went. So there's something called I think it's called intensity interferometry, and that is so basically the idea is that this is really cool to do with the radio telescope, but it would be even cooler if you could do it with an optical telescope because then you have even shorter wavelength and you could get an even better resolution. And you can kind of do that, but the problem is with the radio signal we have the electronics to just kind of record the actual wave. And then do everything this basically in software. With light, we cannot do this, so you have to kind of physically build this correlation, work with like mirrors and stuff. And that's really, really hard. There's a handful of telescopes that can do it, but they have to be fairly close together, and it's incredibly hard to do. But there's another idea where what you could do instead is you don't record the full wavelength or the entire wave, but you just record the time where when a single photon arrives at a certain telescope very precisely. And there will be a correlation between, if you have two telescopes, there will be a correlation between the arrival times of light at these two telescopes, depending on basically what your source looks like exactly. And this has been tested. The problem is that you need a lot of data, so you need a pretty bright source. And most of the really interesting sources are not that bright. So right now it's at the stage where like you can show that this works in principle, but it's not, as far as I know, it's not really done, like it's not at the point where it can actually do something useful, really.
So the intensity is the arrival, you're correlating the arrival times of a photon, which essentially is measured by the intensity.
Yeah, well, so there's these telescopes called Cherenkov telescopes that we're going to talk about in 2 weeks, and they're actually mostly built for gamma rays, but people started using them kind of like when observing conditions were pretty bad, so you couldn't actually use them for their main purpose, and they were kind of free. And with these gamma ray telescopes, you actually measure like individual photons of light reaching your detector, and because of the way they work, just for like the observing gamma rays with them, you want to measure this very precisely.
That's fine. It's very difficult.
Yes, but kind of by accident, they built a telescope that can also do this intensity interferometry. So that's what they currently use for some of the time. But there's, as far as I know, there's no like dedicated intensity interferometer because I think we're quite a long way from that actually being useful, unfortunately. Because it would be pretty cool. Yeah? So
I have a question about the very first slide and something Steker said about the electromagnetic spectrum and the evolution of our eyes to be sensitive to what we now call visible light. So I don't know if this is a physics question or not, or if it's maybe physics meets biology in evolution. Is there anything that physics can say that is peculiar to that particular part of the spectrum that could explain why evolution favored the development of a sensitivity in an organism that ultimately evolved into our eyeballs, as opposed to why that wouldn't happen with microwaves, for example?
Yeah, so I'm pretty sure the answer is the sun. It's that our eyes can, our sun produces a spectrum that our eyes are fairly, that sort of sets the range of what sort of light we're going to be sensitive to, because we're just seeing like sunlight being reflected, right, and off surfaces. Like that's how we see things, is just light being reflected. So my full understanding is that it's because sunlight is and then plus sunlight meets some sort of chemistry and atomic physics of how light gets reflected as different colors.
Well, is that because that part of the spectrum is where the vast majority of the sunlight is?
Yeah, I think it's where it's brightest.
It's not. I mean, it's also emitting other.
Yeah, that's where I think where it's just brightest. So that's where the most available, like we evolved to use what was most available, which is like got sunlight.
And it's also where the atmosphere is most transparent. So if you tried it with microwaves, you just wouldn't see a lot. It would be pretty dark. Yeah?
So that biology question is interesting because not all creatures have the same sensitivity that humans do. Right?
Yeah.
But based partly on their behavior, they might find it more advantageous to see in the infrared. And some creatures do that.
Yes.
So we're all, the peak of the solar spectrum is a big peak, right? 5,500.
Yeah, exactly. Yeah, you can test the theory with different types of organisms and how much light they see, how their eyes evolved.
I have a question
from last week lecture. Okay. In survey, when surveyors, they survey lands, they have this, like a telescope, they are looking. So they really create a triangle. Okay, in triangle, there are three angles and three lines. And if you know three of them, then you can find out the other three.
Yeah.
And so in this case, by moving from one point to point, and they can measure that, this is one side of the triangle, and the telescope will tell them the two angles, and how they calculate how far the object is. And this could be probably what last week you explained.
Yeah, that's basically parallax, yes.
That how far the object is.
Yes.
Okay.
That's, yeah, it's basically the same technique, except instead of moving yourself, you just wait for the Earth to move. But other than that, it's the exact same thing. Yes. Okay, more questions? Yeah? Yeah, you.
What, if any, effect would inflationary theory have on our interpretation of a lot of this data?
Well, I guess that's for you.
Awesome question. So let's see. So inflation, the way you worded the question, asking about how we'd interpret this data, I wish I'd put a power spectrum on one of these slides. But basically, it wouldn't alter, as far as we know, as far as I know, I should say, it wouldn't alter the way that we see the data now. Because right now, sort of, we're looking at the CMB and we're seeing all the temperature fluctuations, and this would tell us something about the gravity fluctuations. So the data we have now is independent, which is why it's so tough to find this B mode signal, because it's totally independent from the density signal that we're familiar with. So what an inflation signal would do is change the model of the universe. And that might have some long tail effects. That's why I'd love to have a spectrum that the cosmic microwave background, the size of these things is characteristic. Like, you can sort of see there's more things of one shape than another. It's not random that there's actually shapes. And as you get to how gravity might affect things at different scales, the further you go out into the power spectrum, the more the effects of gravity are washed away. So the efforts that we're doing now with higher and higher resolutions, not going to tell us anything about gravity, which is actually why we build that kind of goofy, bad moon telescope. It's a half a meter, which is really bad for looking at the moon, but it's very good for looking for this theoretical signal. So that's really, if we can, right now the data tells us there's no signal of inflation. But that's why we have so many of these sort of small telescopes that you'd think, why do you use that? It's because we think that size is about what the B mode signature would be, which is the inflation signature. Great question.
Okay, thank you.